Hey, welcome back, HL chemistry students. This flip lesson is for the HL chemistry students only, and it continues topic 10, 10.4, which is actually HL topic 20.2 in the DP curriculum on synthetic roots. Right? If you remember, there were three additional HL topics for organic chemistry topic 10, right? The first one was organic reactions, which we have already covered in class. Those are the mechanisms of the SN1, SN2, and of the addition to alkenes, mechanistic details. The second topic is this topic here, synthetic roots, and the third topic will be stereoisomerism. So let's get into synthetic roots here. Actually, let's go back here. When you're doing synthesis, you are trying to make a certain compound. In fact, this is how I was trained. I am a synthetic organic chemist. This is exactly how I was trained and educated. And so what does this involve? Well, you're very accustomed to this type of problem. This is the classical organic chemistry problem, where you're given reactants A and B. You're given the reaction conditions. Your challenge is to predict, right, the identity structure of product C. Excuse me, product C. Right? This is the classical problem. And you can see many examples of this type of problem throughout the DP chemistry curriculum, assessments, paper 1, paper 2. Here are three examples right here. Whoops, sorry. These happen to be from paper 1, but you can certainly find many examples in paper 2 as well. Right? What's the major product of the electrophilic addition of hydrogen chloride to propene? So you're given the reactants here, right? And you're given the reaction conditions, and you're to pick the product, predict the product. Over here, what's the major product of the reaction of HBr with but1ene? You're given the reactants, okay, and the conditions. You're to predict the product. In this particular example here, you have sort of a chain reaction or a chain problem, all right, where, but again, you're given the reactants in each case and the conditions, and you're to predict, in this case, X, Y, and Z. Well, you actually don't have to answer X and Y, but you need to know X and Y to answer Z. So you get the idea here. This is the classical organic chemistry problem. But what if we flip the problem around? What if we have the inverse problem, where you're given C, the product, and you have to come up with A and B and the conditions? This is the synthesis format problem, right? You know what you want to make. You know the target. That's the target molecule. Your challenge is to, based on your knowledge of organic reactions, can you find reactants A and B and conditions for reactants A and B that will give the target C. This is the opposite problem, the inverse problem. All right? And in synthesis, what we generally have is we have a series of these problems. So in other words, we might have some distant target, molecule F, right? And we then have to construct a pathway to get to F, again, given our library understanding of organic reactions. Now, your library understanding of organic reactions is very, very limited. However, you do know enough organic reactions to be able to tackle these types of problems, and you'll have to, because you'll have these types of problems, and IB wouldn't give you these problems if you didn't have that library knowledge. So let's see what this involves. How do we tackle a multi-step synthesis problem? How do we tackle that? Okay, here are some examples. These are from your textbook, right? These are all examples of multi-step synthesis. And we're going to look at this one here, 10.3, in detail as an example. This is called retrosynthetic analysis. Retro, backwards. This is working backwards. Working backwards, right? Knowing that you want to make F, can you work backwards and construct reactions that will eventually lead to molecule F? Okay? And just by way of some history, you won't be tested on this, but this is very, very, very close to my heart, because I worked under Professor Corey at Harvard as part of my PhD degree. And Professor Corey, pictured here, is 91 and is still goes to work every day. He lives several blocks from the chemistry department at Harvard. He walks to work every day, rain or shine, including lots and lots of snow. Harvard University is in Boston, Massachusetts. They get a lot of snow there in the winter. It's very cold. He's 91. He still walks to work. He still puts in a full day's work. He still has students that he works with and postdoctoral scientists. He won the Nobel Prize in chemistry in 1990 for his pioneering work in retrosynthesis. So I have to mention this because it's part of my history as well. Okay. And this is what Professor Corey pioneered. He pioneered the development of what's called a retrosynthesis tree. It's a upside down tree. If you picture an upside down tree, right, where you have the trunk of the tree, and then you have the branches of the tree and the leaves of the tree, and it starts to expand and get larger and larger as you go down. That's basically what we have. That's basically the conceptual aspect of this, where you know your target, okay, and so that might be a new drug. That might be a new material for a new plastic. It could be lots of different things, but you know what you want to make or synthesize. What you do then is you come up with, say, the precursors. That's what P means. Say there are 5 precursor molecules that in one step, you know from your knowledge of organic chemistry reactions can be converted to the target. These are retrosynthesis arrows. What they mean is that I know that this target molecule can come from molecule P3 or can come from molecule P4 in one step. Then you do this all over again with each of these precursors. You see what's going to happen here is you're going to generate, right, a large number of precursor molecules and a large number of different possible paths to the target. And then it's up to the synthetic organic chemist to choose the best path. You're not going to have to do this, but you are going to, again, with your limited library understanding of organic chemical reactions, you are going to basically go through this process, and I'll show you how this works. So let's go right to an example. This is example 10.3, right from your textbook, Cambridge textbook. Design a reaction sequence using balanced chemical equations for the conversion of propene to propanoic acid. How do you do this problem? Right? The first thing that you do in step 1, now this is retrosynthesis step 1. We're working backwards. Because the first thing you're going to do is you're going to write this problem in the form of a chemical reaction equation, and that's what I've done here in step 1. Knowing that I'm starting with propene, and you will generally be told what you're starting with. You generally aren't just going to be given a target and a blank sheet of paper. You're generally told what you're starting with. But notice you don't know any organic reaction that can take propene and give you propanoic acid in one step. You don't know of any such reaction. Okay. In fact, in fact, I don't know of any reaction that can do this in one step. So this is a multi-step synthesis problem. And so what do? Well, you start generating the precursors, the immediate precursors. Well, propanol is an immediate precursor of propanoic acid because it can be oxidized with chromium-6 in one step. What else is an immediate precursor of propanoic acid? Well, the ester, methylpropanoate. Remember esters. Esters can be hydrolyzed, that's the reverse of their formation, to give the carboxylic acid and the alcohol. So methylpropanoate, the ester, is an immediate precursor of the target molecule, propanoic acid. Then you do this again. You say, well, how do I make propanol? How do I make one propanol? Well, if I had, one bromopropane, I could use nucleophilic displacement, SN2 nucleophilic displacement, which is a reaction that you know, and that would give me in one step one propanol, right? How do I make methylpropanoate? And here's where that pathway goes away, because methylpropanoate is made from the carboxylic acid. Well, that's circular because you need to make the carboxylic acid. So now we can focus only on this path here, and we can ignore this other precursor path here. And so now we ask the question, well, how do we make one bromopropane? Well, if we had propane and bromine, we could use light, free radical halogenation, bromination, and we would get a mixture of 1 bromo and 2 bromopropane. And that's okay, because we can separate these two compounds. You can assume that you can separate these, right? And then we're asking the question, well then, how do we make propane? And at this point, we might see the connection between propane, the propane precursor, okay, which is down here in this tree, and what's called the starting material. This is called the starting material, right? We have propene and propane, and we know that we can hydrogenate. We can catalytically hydrogenate propene to make propane. And that completes the problem because we have connected the target molecule, propanoic acid, to the starting material. Now we have to reassemble the equations in the forward sense to solve the problem. And that's done here in this last slide. So step one would be you go into the lab and you hydrogenate propene, under the proper conditions to give propane. Then you do free radical bromination of propane and get a mixture of 1 and 2 bromopropane. Then you take the 1 bromopropane and do nucleophilic SN2 displacement with the hydroxide nucleophile to make 1 propanol, and finally you oxidize 1 propanol, under the right conditions to propanoic acid, and you have solved the problem. You have solved this problem. This is basically what's involved in this whole topic. All the way back here. That's what's involved. So we're going to practice some more. In fact, you're going to, for homework, HL students, you are going to try problems 10.2, problems 40, and problems 41, as homework. 10.2, 40, and 41. Let's see how you do. Have a good evening. I think that's the end of that, right? That is the end of that. Okay.